In the past few lectures, we have looked at values of different types in Python, starting with the numbers, then moving on to the booleans, and then sequences such as strings and lists. Now let's go back to the order in which statements are executed. Remember, we said that a typical Python program will have a collection of function definitions followed by a bunch of statements. So in general, the Python interpreter will read whatever we give it from top to bottom. So when it sees a definition of a function, it will digest it but not execute it. We will look at function definitions in more detail very soon. And when we now come to something which is not a definition, then Python will try to execute it. This in turn could involve invoking a function, in which case the statements which define the function will be executed and so on. However, if we have this kind of a rigid straight line execution of our program, then we can only do limited things. This means we have an inflexible sequence of steps that we always follow regardless of what we want to do. Now in many situations, in many realistic situations, we need to vary the next step according to what has happened so far and according to the current values that we see. Let us look at a real life example. So supposing you're packing your things to leave for the bus stop in the morning. Now whether or not you take an umbrella with you will depend on whether you think it is going to rain that day. If you carry the umbrella all the time, then your bag becomes heavy. If you don't carry the umbrella ever, then you risk the chance of being wet. So you would stop at this point and see, in whatever way, by reading the weather forecast or looking out of the window, is it likely to rain today? If it is likely to rain, ensure that the umbrella is in your bag, put it in if it's not there, or leave it in if it's already there. If it is not likely to rain, ensure the umbrella is not in the bag. If it's not there, it's fine, otherwise take it out. So this kind of execution, which varies the order in which statements are executed, is referred to in programming languages as control flow. So there are three fundamental things, all of which we have seen informally in the GCD case. One is what we just described, the conditional execution. The other is when we want to repeat something a fixed number of times, and this number of times is known in advance. We want to carry 10 boxes from this room to that room. So 10 times we carry one box at a time from here to there. On the other hand, sometimes we may want to repeat something where the number of repetitions is not known in advance. Suppose we put sugar in our teacup and we want to stir it till the sugar dissolves. So what we will do is stir it once, check if there is still sugar, stir it again, check if there is still sugar, and so on. And as the sugar dissolves, finally after one round, we will find there is no sugar at the bottom of the cup and we will stop stirring. So here we will repeat the stirring action a number of times, but we will not know in advance whether we have to stir it twice or 5 times. We will stir until the sugar dissolves. So let's begin with conditional execution. So conditional execution in Python is written, as we saw, using the if statement. So we have if, then we have a conditional expression which returns a value true or false, typically a comparison, but it could also be invoking a function which returns true or false, for example. And we have this colon which indicates the end of the condition. And then the statement to be executed conditionally is indented. So it is set off from the left so that Python knows that this statement is governed by this condition. So we make this simultaneous assignment of m taking the old value of n and n taking the value of m divided by n only if m divided by n currently is not 0. So the second statement is executed conditionally only if the condition evaluates to true, and indentation demarcates the body of the if. The body refers to those statements which are governed by the condition that we have just checked. So let us look at a small kind of illustration of this. Suppose we have code which looks as follows. We have if condition, then we have two indented statements, statement 1 and statement 2, and then we have a third statement which is not indented. So the indentation tells Python that these two statements are conditionally executed depending on the value of this condition. However, statement 3 is not governed by this condition because it is pushed out to the same level as the if. So by describing where your text lies, you can decide the beginning and the end of what is governed by this condition. In a conventional programming language, you would have some kind of punctuation, typically something like a brace, to indicate the beginning and the end of the block which is governed by the condition. So one of the nice things about Python, which makes it easier to learn and to use and read, is the dispensation with many of these punctuations and syntactic things which make programming languages difficult to understand. So when you're trying to learn a programming language, you would like to start programming and not spend a lot of time understanding where to put colons, semicolons, open braces and close braces and so on. So Python tries to minimize this, and that makes it an attractive language both to learn and to write code in if you're doing certain kinds of things. So Python will not have this, and then we will see a much cleaner program as a result. One thing we have emphasized before, and I'll say it again, is that this indentation has to be uniform. In other words, it must be the same number of spaces. And the most dangerous thing you can do is to use a mixture of tabs and spaces. When you press the tab on your keyboard, it inserts some number of spaces which might look equal to you when you see it on the screen, but Python does not confuse tabs and spaces. So one tab is not going to be equal to 3 spaces or 4 spaces or whatever you see on the screen. And the more worrying thing is that Python will give you some kind of error message which is not very easy to understand. So it's quite useful to not get into the situation by remembering to always use exactly some uniform strategy, for example 2 spaces, to indent whenever you have such a nested block. So quite often we have two alternatives, one to be taken if the condition is true and the other to be taken if the condition is not true. So if it is likely to rain, ensure the umbrella is in the bag, else ensure the umbrella is not in the bag. Right? So in this case, for example, if the remainder is not 0, continue with new values for m and n. If the remainder is 0, then we have found the GCD, namely the smaller of the two values. So this is indicated using the special word else, which is like the English else, again with a colon. And again we have nesting to indicate what goes into the else, and the if and the else should be nested at the same level. The else is optional, so we could have the if without the else. Technically speaking, the condition that we put into an if statement must be an expression that explicitly returns a Boolean value, true or false. But like many other programming languages, Python relaxes this a little bit and allows different types of expressions which have different values, like the types we have seen so far, like numbers and lists, to also be interpreted as true or false. In particular, any number, any expression which returns a number 0, any numeric expression of value 0 is treated as false. Similarly, any empty sequence, such as the empty string or the empty list, is also treated as false. And anything which is not this case, so if I have a non-zero value as a number, or if I have a non-empty string, a string with 7 characters, or a non-empty list, a list with 3 values, then all of these would be interpreted as true if I just stick them into a condition. So this can simplify our expressions and our code. So instead of saying m%n, as we said before, m%n not equal to 0. So remember, if it is not equal to 0, then it is true. Right? So when it is not equal to 0, it is true. So if this condition holds, the same as asking whether m%n is a non-zero value. And if it is non-zero value, we want to replace m and n. So we can just write if m%n. Right? So this is a shortcut. Now use it with care. Sometimes if you are used to it and if you are familiar with what's going on, this can simplify the way you write things. But if you are not familiar with what you're going on, you can make mistakes. So if you're in doubt, write the full comparison. If you're not in doubt, or if it's very obvious, then go with the shortcut. Here is a very common situation that occurs. Sometimes we don't want to check between one of two conditions, but one of many conditions. So supposing we have a value x, a name x, which can take a value 1, 2, 3 or 4, and depending on whether it's 1, 2, 3 or 4, we want to do 4 different things which we called f1, f2, f3 and f4. So if we simulate this 4-way choice using a if and else, then we have to make some comparison first. So supposing we first check if x is equal to 1, then we invoke f1. If x is not 1, then it's one of the others. So all of this goes into an else and everything gets nested. Then we check, in this case, if x is equal to 2, then we do f2. Otherwise, we have 3 or 4. So now all of this is nested once again. And finally, we have x is equal to 3 or not 3. So this is x is equal to 4, and then we are done. But the main problem with this is that, first of all, this code is getting indented. So as you go into this nested if structure to simulate this multi-way branch, right, we have essentially a 4-way branch. X could take one of 4 values. For each of these 4 values, you want to do 4 different things. So if we simulate it by taking 3 two-way decisions, we check 1 or not 1, then we check 2 or not 2, and then we check 3 or not 3. Then we have this ugly nesting, and secondly, we have this else followed immediately by an if. Right? So Python has a shortcut for this, which is to combine the else and the if into a second check, elif. So this on the right is exactly the same as the left as far as Python is concerned. It checks the condition x equal to 1. If x is equal to 1, then it will invoke f1. Otherwise, it will invoke the rest. Now the rest, we have just collapsed the else and the if to directly check a new condition. If this condition holds, then this works. Otherwise, it will check the rest and so on. So we can replace nested else if by elif in this way. And it makes the code more readable because it tells us that we are actually doing a multi-way check. And notice that the last word in elif is again an else. So if you have, say, 7 different options and you're only doing special things for 1, 2, 3, and 4, 5, 6, 7 are all the same, then we can use else. We don't have to explicitly enumerate all the other options. So we have a number of explicit conditions that we check. So by the way, this, I noticed is a typo, they should not be here. Okay. So we have a number of explicit conditions we check with if and a sequence of elifs. And finally, we have an else. The else again is optional, like it is with a normal if. But the main thing is it avoids this long indentation sequence, which makes the code very difficult to read later on. So the first type of control flow which we have seen is conditional execution, and the other type is loops. So in a loop, we want to do something a repeated number of times. So the most basic requirement is do something a fixed number of times. So here, for instance, we have the statement for, which is the keyword in Python. So what Python says is take a new name and let it run through a sequence of values, and for each value in the sequence, execute this once. Right? So this is in sequence, it's multiplying y by 1, then the result by 2, then the result by 3, and so on. So at the end of this, we'll have y times 1 times 2 times 3 times 4, and we'll have z plus 1 plus 1 plus 1 plus 1 4 times, because each time we're adding 1 to z. So this will be the outcome of this loop. So the main thing is exactly like if we have indentation to mark the body of a loop. So the most common case for repeating things is to do something exactly n times. So instead of writing out a list 1 to n, what we saw is that we can generate something equivalent to this list by using this built-in function range. So range 0, 1, we said, starts at 0 and generates a sequence of the form 0, 1, 2, stopping at n minus 1. So this is similar to the positional convention in Python, which says that the positions in the list go from 0 to the length of the list minus 1. So range also doesn't go from 0 to n, but 0 to n minus 1. So instead of writing for I in a list, we can write for I in a range. And this is, from the point of view of Python, the same thing. Either we can let this new name range over an explicit list or an implicit sequence given by the range function. So in general, range ij, like a slice I to j, starts at I and goes up to j minus 1. So we can also have range functions which count down, and we can have range functions which skip a value. We can do every alternate value and so on. We will see these variations on range a little later. But for now, just note that we can either have a for statement which explicitly goes through a list of values. So we can give a list and ask for to go through each value in that list. Or we can generate a sequence of n values by using the range function. So let's look at a simple example of this. Suppose we want to find all the factors of a number n, all numbers that divide n without a remainder. So as we recalled when we did GCD, right, all the divisors or factors of a number must lie between 1 and n. We cannot have any number bigger than n which is a factor of n. So one simple way to check the list of factors is to try every number from 1 to n and see if it divides. So here is a very simple function for it. So we define a function called factors of n, which is going to give back a list of all the factors. So internally we use a name flist to record this list. So the flist, the list of factors is initially empty. And now, keeping in mind that all the factors lie between 1 and n, we generate in sequence all the numbers from 1 to n. And remember, this requires the upper bound of the range to be n plus 1, because the range function stops 1 below the number which is the right hand side. So this will generate the sequence 1, 2, 3 up to n. And what we check is, if there is no remainder when n is divided by I, then we add I to this list. And remember that plus for a list and for a sequence is concatenation. It actually adds a value to a list. And this allows us to return a new list. Okay, so at the end of this, we have computed all the factors of n and returned them as a list. But as we said at the beginning of today's lecture, sometimes we want to do something some number of times without knowing the number of times in advance, like stirring the sugar in the cup. So we saw an example of this with the GCD. So what we did was, we have another statement like for called while. So while executes something so long as a condition holds. So we execute this body so long as this condition evaluates to true. And then when we have finished executing this, we come back and check again whether this condition is true or not. So the danger is that every time we come back, the condition will be true and this thing will never end. In the for case, we know in advance that it will execute exactly as many times as the length of the sequence that we started with. So when we start a for loop, we give a fixed sequence. That fixed sequence has a fixed length, and so we must terminate the loop in that many executions. In a while, we come back, we check the condition again, but there is every possibility that the condition will never become true. So we have to ensure when we write a while loop that somehow this sequence of statements we execute inside the while must eventually make this thing to be false. Because if this thing never becomes false, the loop will never terminate. So the example we saw with GCD was a variation of what we wrote so far. So we first, of course, check and swap so that the bigger number is first. And now we check whether the bigger number is divisible by the smaller number. So long as this is not the case, we exchange values for m and n. We make m point to the smaller number n, and we make n point to the remainder, which will be still smaller. And eventually, this thing will become false. We will get the situation where n divides m and the remainder is 0. And at that point, we have found the GCD. Okay? So this is a simple example. Of course, remember that by our earlier convention, we could also write this as while m percent n make this thing. Right? So we don't need this explicit not equal to 0, because the value m percent n, if it is not 0, is treated as true and the loop will go one more time. But now in some situations, it may or may not be so easy to read this. So it might be useful to just say explicitly not equal to 0, just to illustrate to yourself and to the person reading your code what's going on. So to summarize, a Python interpreter normally executes code from top to bottom in sequence. So we can alter the control flow in 3 ways we have seen. One is using the if statement, which conditionally executes, and this extends to the elif, okay, which allows us to do a multi-way branch. Then there is the for statement, which allows us to repeat something a fixed number of times by providing a list or a sequence of values from range. And then we have a repetition, which is based on a condition using a while statement, where we put a condition and then the body is executed each time the condition is checked again. So long as it's true, the body keeps repeating.